So it's great to have Madhur as our Research TTIC speaker today. And as you know, Madhur is an NCR faculty member here. And Madhur will be talking about list decoding. So,
all right. Okay. So we start. Apologies. Some of you have probably heard me talk about list decoding or expander-based codes in multiple previous years. But then coding theory is all about redundancies. So we'll do that. And I'll still remind you of the basic definitions, especially for the first-year students. But hopefully there'll be something new. Okay. And I'll talk about something which is joint work with Shashank, who was a student until a couple of years ago and now is at IIS. So we'll unroll the title slowly, but let's start with codes. And this is kind of my usual slide on codes, that we want to communicate something. And in particular, what we mean here are error correcting codes. So when we try to communicate, maybe we think of an adversary as introducing errors. And adversary is really a proxy for an error process which we don't understand and maybe don't want to make too many modeling assumptions about. So it could be just kind of some black box algorithm for which we don't really know the code and we don't want to make too many assumptions, except maybe some bound on how many errors it can make, because otherwise it's kind of hopeless if you don't make any assumptions at all about errors. Okay, and suppose we want to communicate 3 bits and the kind of adversary can corrupt any 1 bit, and in particular something like this. Then we want to figure out what's a good way of encoding the message, or like what's a better way of sending this message so that even if any 1 bit is corrupted, you receive the intended message. And here's one way of doing it: just repeat everything 3 times. And of course, if you and I both know that everything is repeated 3 times, we can always figure out the mistake. Okay, and sort of coding theory is about, can we do this better? And in particular, should say that, okay, if you haven't seen codes before, you have actually seen them before. So first, anything you have ever said is an error correcting code. I'm just making funny sounds and you're kind of converting them into sort of letters and first of all sounds in your head. And if Avrim or Sasha were to make the same sounds, they would sound different, but you could correct them to the same letters and maybe the same concepts in English and so on. It's used for any kind of electronic communication, and also used in kind of many devices that you use, and maybe for future technologies like quantum computing and so on. So, and the difference between maybe what the first example was and the others is that in the second and third setting, we get to design these codes. In the first one, we didn't quite design sort of vocal cords and the way English language work, it evolved, but in coding theory, we'll say, what can we do if we get to design? And okay, let's make this a little more formal. So we'll think of codes as maybe a sequence of bits or a sequence of symbols. And we'll think of these symbols as in a field of size 2 or more generally of size q, which we'll call the alphabet size. The length of the sequence is what we call the block length of a code word, and a code is a collection of such code words. So it's a subset of f2 to the n or fq to the n. And we'll measure distance between these code words as kind of the fraction of the n positions in which they differ. So if you have 2 such code words, we'll take the Hamming distance, except we'll divide by n so that we just have numbers between 0 and 1 and don't have to remember the n. Stop me at any point if something is unclear. These are probably definitions which you've seen, but yeah, just want to make sure we all are on the same page. Okay, and so define the distance of a code as kind of the worst case distance between any 2 code words. So the closest non-identical code words, what is the distance between them? And if this is some fraction delta, then if the adversary makes less than delta over 2 kind of corruptions or changes less than delta over 2 symbols, we can always, in principle, figure out the nearest unique code word, which was age-ended. Okay, so this is called unique decoding. This is just, in principle, possible, but it's always or often a very non-trivial algorithmic problem to actually find this kind of a code word. And this is what we think of as the algorithmic problem of unique decoding. Any questions? Yeah.
So the assumption that the adversary is limited is in the fraction of positions it can change.
Yes.
That's what's making larger Q easier than smaller Q. In other words, like glomming larger Qs with glomming more stuff per thing.
Yeah. So yeah, that's a good point. So larger Q, you can think of it as basically an extra assumption on the error model. So if I have Q which is 8, just means that I kind of clump my bits into groups of 3 and I say either the entire group is corrupted or not, and I'm now counting the number of groups that are corrupted rather than the number of bits. And that also kind of brings an interesting point that maybe we would like to work with as small a Q as possible, because the larger the Q is, the stronger assumption that, okay, we have to really talk about blocks of this size. And then we'll come back to this point, but thanks. Okay, and this is the decoding problem that we talked about, of unique decoding, if we have less than delta over 2 fraction of errors. Yeah.
Why is our alphabet a field?
Sorry?
Why is our alphabet a field and not just a random set?
It doesn't always have to be, but I'll define codes, or I'll kind of work with codes which have some linear operations in them, so it will be useful to give a field. And so field makes it, so in a moment I'll kind of talk about codes which are subspaces, and these codes are easier to describe in the following sense. So if I have an arbitrary, say, subset of Q to the n, I have to just write down all the code words. But if it's a subspace, I can just write down a basis for that subspace, and it has a much more succinct description. And it also has some other nice properties, but these are called linear codes, which are subspaces of fq to the n. And kind of today we'll kind of restrict our attention to this, although it's not strictly important for the algorithms. I mean, so we don't necessarily need it, they're just kind of more convenient to work with. Other questions? Yeah, so I kind of made this with an assumption that it's a field, but it doesn't always have to be. In fact, for the algorithms I describe, it doesn't need to be. Alright. And today we'll talk about list decoding, which is basically a problem which says, okay, maybe I have more errors, let's say a row fraction of errors. The row is more than delta over 2, so unique decoding may not be possible. Is it possible to maybe find a small list of possible code words which were intended? And then and now there are two issues. Like one, we don't even know if the list is going to be small, so someone has to prove this, or we have to prove it. And this is the combinatorial aspect of list decoding. And then even if the lists are small, that doesn't mean it's easy to find them. Even in the unique decoding case, it was not always clear if list of size 1 is easy to find. So, and list decoding, again, can be a proxy for things. We can think of it as, okay, maybe I have some side information about this, which I don't want to include in the model of the code because it's kind of more complicated. So, yeah, maybe you'll give me 5 options, and I kind of know that, okay, usually an image will not have people standing upside down, so maybe I'll be able to figure out the right option, or at least be able to distinguish between these options using some other side information, which again is kind of harder to model in the definition of the code. This is one way of thinking about list decoding. There are other ways, and in particular in complexity theories, sometimes it's okay to just pick a random element of the list. Okay, and now we need to, so yeah, you should have maybe taught me in list decoding, because somehow the problem of list decoding is not entirely well defined unless you know that the distance of the code I'm telling you is the right number, or like maybe is as large as possible depending on the code or depending on other parameters. But otherwise I can lie. I can just tell you that the distance is, I don't know, 0.2 when it's actually 0.4, and then I always have lists of size 1, and I'll just apply a unique decoding algorithm and just pretend that it's list decoding. So we need to really understand how large this delta can be. And there's one bound which says that delta is always at most 1 minus r. This is called the singleton bound. And this is true when the alphabet size is at least somewhat large, and we'll come back to how large.
Do you remind what is capital R?
So, sorry, capital R is the rate of the code. Maybe I didn't define it or skip the. Okay, my apologies. Capital R is the rate of the code. So it's the log of the size of the code divided by the log of the size of the entire space, which is q to the n.
Codimension.
Sorry?
Codimension.
For linear codes, it would be the log of the code. No, just code dimension, not log. Right. So this is kind of a measure of how much redundancy the code has. If the code has q to the n over 2 code words and the actual space is of size q to the n, then the rate would be half, saying that basically we are off by this factor of 1/2 in the exponent. Okay. And so it makes sense that if I have small rate, then I have very few code words and they can be very far apart. So the distance can be large. And if I want the rate to be really large, then I have lots of code words and it's kind of harder to pack them very far apart from each other. And singleton bound kind of captures this. Says that delta is at most 1 minus r, and there are codes which actually achieve this. And so, for example, classical codes, Reed-Solomon codes, which maybe you heard about in information theory if you took it, otherwise talk to me next year, have this property that they actually get delta equals 1 minus r, in fact, even a more sort of non-asymptotic version, not just as fractions. The problem with Reed-Solomon codes is that they're defined by kind of evaluating polynomials at different, so every symbol is an evaluation of a polynomial. But if you have n symbols, you need to have n points to evaluate these polynomials in, and so the field size needs to be super large, at least as large as n, okay, which is the block length, or should have been capital N. And these are, again, celebrated codes, but the alphabet size, kind of going back to what Abram was saying, this is kind of an assumption saying that you have blocks of size log n, and you have to really make assumptions about either the entire block is corrupted or not. And then this block, log n, is somewhat large. But these codes come with excellent properties. There's a lot of nice things known about list decoding. And in particular, there are algorithms which can list decode up to a radius known as 1 minus root r, which is called the Johnson bound. This is a radius up to which we know that any code actually has a bounded list size. So,
bounded you mean an absolute constant depending only on absolute constant capital R?
So for any epsilon, the list size in 1 minus root r minus epsilon radius will be bounded as a function of epsilon, but not of n.
You have to go a bit below Johnson bound.
But if you want 1 minus root r, it can still be bounded as a function of n, but a polynomial function of n.
A polynomial function.
Yeah.
And
So-
epsilon also, yeah?
Sorry?
And epsilon also.
Yes, it's 1 over epsilon square. Okay. And so, okay, so Johnson bound is kind of a nice threshold because up to there the combinatorial problem is always easy. We know the list size is bounded, but finding it is a whole other story. And these are like celebrated works by Sudan and Gurswami Sudan, which kind of started this whole area of list decoding. I mean, this was defined before, but these were the first non-trivial algorithms, and they reached up to Johnson bound for the Reed-Solomon codes. What's the row? Sorry, rho is the list decoding radius. So the number of corruptions which I want to handle with list decoding, a fraction of corruptions. Yeah, sorry. So there are a couple of parameters. I try to include them in pictures, but delta is the distance of the code. Rho is always the radius or the list decoding sort of the fraction of errors at which I'm trying to do list decoding. And the Johnson bound, which is some function g of delta, but when delta is 1 minus r, Johnson bound is 1 minus root r. This is kind of an intermediate radius up to which we always know combinatorially the list size is bounded. Algorithmic problems are not really. And beyond this, it's kind of the Wild West, so we don't really know even if combinatorially the list is bounded. Okay. So these are kind of two maybe regime of parameters up to Johnson bound and beyond. And Johnson bound is always somewhere between delta, which is the distance of the code, which is the maximum we can hope for in some sense, and delta over 2, which is the unit. Okay. Any questions at this point? Okay. So you don't need too much about Reed-Solomon codes. I just kind of mentioned them to say that, okay, these parameters are achievable and this is doable. In fact, there are codes which can go beyond the Johnson bound, and these are again defined using polynomials, so-called correlated Reed-Solomon or folded Reed-Solomon codes. In fact, folded Reed-Solomon codes do something even more interesting, you can go all the way up to the distance or 1 minus r, which is the maximum possible distance, and again up to epsilon. And there are also later constructions called multiplicity codes, which also achieve this maximum possible list decoding radius, also known as list decoding capacity. So that's the best we can hope for. And I mean, random codes often kind of do the best possible thing in many settings, but it's hard to have algorithms. And these are algebraic constructions which actually achieve these list decoding capacity kind of results. Okay. Any questions? Okay. So I described that, okay, we can basically do list decoding all the way up to maximum possible radius, bounded list sizes, explicit constructions of codes. There are a couple of issues with this. One, okay, like the first point I'll try, but the later parts, one, the alphabet size, which is again comes down to this block length, is a problem. So the alphabet size for Reed-Solomon codes, I already said was larger than n, which is the block length. And for folded Reed-Solomon, if you want to be epsilon close to 1 minus r or epsilon close to capacity, then it needs to be n to the 1 over epsilon, so even larger. The other is sometimes we don't just want error correction, we want error correcting codes with certain other kind of structural properties. And one popular example is LDPC property, which says that, I mean, low density parity checks, which just kind of says that I should be able to check if a code word is valid by doing some sort of spot checks, lots of them. But each check should be only on small number of positions in the code. So that's the low density part. And this is particularly desirable when people are working with quantum codes because they want to somehow implement this using physical connections of qubits, and then you don't want too many qubits in these connections. You also want some geometric locality, but I'll not worry about that. Okay. And the third, like the other point which I sort of think of more as a philosophical question is that do we really need algebraic structure for list decoding, particularly beyond Johnson bound where there's sort of all these constructions to rely on algebra? And the answer will be no, as you might have guessed from the way it was phrased, and then we'll sort of go beyond it using expander graphs. So let me remind you what expander graphs are, and then we'll then talk about how to construct codes using them. In this talk, we'll think of bipartite balanced expanders. So we'll have sort of two sets of vertices on the left and right, each of size n. We'll think of a degree d or d regular bipartite graph. Every vertex has degree d. We'll think of d as a constant. And we'll say it's a lambda expander if the second singular value of the kind of bipartite adjacency matrix of this is at most lambda. Okay. And we normalize, so we divide by d. D is the maximum possible, is the number of entries in any row. So the singular value of the unnormalized matrix will be at most d. After normalization, it will be 1. And this lambda now, as written, is a number between 0 and 1. So the smaller it is, the better we'll think of the expansion. And actually, all we need is that in expander graphs, we can estimate the number of edges between any set S and any T fairly accurately. So d over n times the size of product of these sets will be, if they were kind of, if the edges were thrown randomly, then this would be the expected number. And there is a small error which is controlled by how small this lambda n. D times n is the total number of edges. So if lambda is 0.01, it just means that the error is at most 1 over 100 times the total number of edges.
Sorry, lowercase n capital.
Oh, I'm sorry. No, it's all capital N. Sorry. Yeah. My apologies. Yeah, I just at some point changed the block length to capital N, and that was. Oh. All right. So now, how do we define codes using expander graphs? There are lots of constructions. Let me tell you one, then I'll tell you another one later. But this is a kind of not just a single construction, but a family. And this goes back to Sipser and Spielman from 30 years ago. And the one I'm describing is a slight variant by Zamor, where you think of bits or symbols of the codes as sitting on the edges. And now, every vertex kind of has a little code in F2 to the D, kind of a very small one. And we'll think of this as a subspace, so a linear code. And we are going to look at all possible collections of bits on edges which satisfy the property that when every vertex looks at its own neighborhood, the d bits in its neighborhood, they are in this little code C sub n, or what's called the inner code. And this is kind of a very small object of size d, and you can use it to define this much larger object, which is a code which now lives in the space of f2 to the number of edges, which is d times. And if the C sub n is a subspace, then you can think of it as a kernel of some matrix. And so in particular, the entire code is defined by saying every vertex just kind of looks at its neighbors, multiplies them by h, and sees if the result is 0. This is just a valid check for every kind of labeling in the neighborhood of every vertex being in the inner code. And these are low density checks in the sense that every check only depends on d bits in the neighborhood of this vertex. So these are in particular LDPC codes. They only depend on the local views of vertices. Any questions? Okay, so this is one construction, and there are other variants of this. In fact, it's been used in lots of interesting ways, including kind of codes over reals with interesting geometric properties, recent constructions of so-called locally testable codes, where these LDPC checks, you don't even need to check all of them, but to do some robust check, if you only check constant number of them, then you can say if something is either a code word or far from a code word. And also recent constructions of quantum LDPC codes, which are slightly more involved objects. They are basically two codes with some interesting connections between them or some properties, or at least the ones in these constructions. Okay, we'll not worry about these fancier versions. We'll just think of the simpler one. In fact, I'll simplify it even more. But these are just examples to say how to construct codes using expander graphs. And then there are lots of well-studied constructions of this one. Okay.
Quick question. Yeah. So when the vertex looks at all the neighbors, like what is the ordering? Is it also specified for this vertex?
Oh, thank you.
Just for the
let's assume we have a predetermined ordering on all the d times n edges. Mm-hmm. And so every vertex kind of just takes that ordering and for the subset of vertices of edges it sees. Yeah, thanks. There is an ordering needed, but let's say we fix it once and for all.
It won't help or it won't hurt if every vertex has its own ordering and say maybe inconsistent.
It should be fine. I mean,
should be fine. Yeah.
Should be fine. It's especially because if I'm looking from the left, the edges incident at all left vertices are disjoint, so they can but I mean, there are also right vertices, so there is some.
Are sitting on vertices. Yeah. So, okay.
Right. Thank you.
Sorry.
Okay, good. So that's one way of defining codes using expanders, and these are, as I said, kind of very classical constructions studied for a long time, and we know excellent kind of decoding algorithms for these. In fact, they have linear time, even parallelizable unique decoding algorithms. The construction for Zemmour had a parallel algorithm. You can decode them via linear programs, or you can decode them via message passing based algorithms. Okay. And so these are great codes in some sense for decoding. The issue with these, and in fact they were designed to have kind of linear time unique decoding algorithms. The problem is, for list decoding, they kind of came up short, at least until recently. So there was no list decoding known for these codes. And maybe a while ago I talked about an algorithm which actually gives list decoding for the Sipser-Spielman kind of codes and many variations of these using semi-definite programs. And my fear was always that if I'm sort of talking to someone who designed a unique decoding algorithm running in linear time, parallelizable, and I tell them you need to solve an SDP of size n to the 100, they'll kind of punch me in the face. So now I try to rectify a little bit, and then we'll talk about, and also these decoding algorithms worked up to Johnson bound. Okay, so at the point where we knew that combinatorially the list size was bounded. And now, today I can tell you about algorithms which actually run in near linear time, so n times log square n. You can think of that. I mean, it's not log, but log square. It's not a bad exponent. Can actually go beyond the Johnson bound. So you have to choose this inner code properly in the design parameters of this construction to ensure this. But you can go up to arbitrarily close to the distance delta, so it not only kind of is an algorithm, it actually also tells you how to bound the list size combinatorially. And it also works for some extensions or some generalizations of list decoding called list recovery and so on, which we'll not talk about today. And I should say, there's a concurrent work of Fernando Geronimo and Aman Singh, which also gets basically the same results, slight differences, but yeah, it also gets near linear time list decoding. Okay. Any questions about the statement of the result before we proceed? Okay. So I'll actually tell you the algorithm for a slightly different code called AEL codes, which I'll describe in a minute, where the algorithm becomes slightly simpler. I mean, it's the same algorithm, it also works for AEL codes and this. So let me tell you what those codes are. And in fact, you instantiate it correctly, you can kind of think of them as coming from this parallel construction, but let's not worry about it. Okay. So these are codes based on a way to amplify distance of codes or kind of improve codes. And this again is a classical construction going back more than 30 years due to Alan Edmonds and Ruby. And you should think of it as sort of like the Tanner kind of code construction with this inner code only on one side. So it's like half of the previous construction with slight twists. So you think of symbols labeling the left vertices as coming from some starting base codes, which we'll call C0. Okay. This base code doesn't need any properties except maybe we'll think of the rate of this code as very high. So it has, but the distance can be really bad, doesn't matter. It has to be just some constant. Then we'll encode every symbol using this inner code, which maps, let's say, a symbol of this outer code or this base code to d bits. So every vertex still sees a code word of C in its neighborhood, it put it there. So it's just edges will still be labeled by this inner code. And the right hand side vertices don't do any checks or anything. They just, the left hand side vertices maybe will send these symbols, the right hand side vertices just collect. So the whole code, which I like to call it just a repackaging operation. The one important thing is that we think of the d bits collected by the right hand side vertices as one big symbol. So it's a symbol of size 2 to the d. And now they will just write down these n symbols, each of size 2 to the d. We just basically float through this graph. And the alphabet size now is 2 to the d. Again, d is a constant, so this is not terribly large. It will be easier to describe some algorithms here, although they also work for alphabet 2, which was the Tanner code construction that I described. So you don't really need even this 2 to the d, but it makes my life a little easier. Okay. Any questions about this code construction? You still have this inner code which encodes every symbol. This time, these symbols come from some starting base code C0. And the left vertices just encode these symbols, send them over, the right guys just collect them. That's all that happens. Any questions? Okay. This code actually is awesome. It kind of does a lot of nice things. And in particular, can show that as long as the starting base code has high rate, close to 1, the new code that we construct by just kind of writing down these right symbols essentially inherits the properties of the inner code. So if the inner code kind of had delta which was very large compared to the rate of that code, or like 1 minus r, which is maximum possible, then the same is true for the global code, again up to this epsilon. And I'll say for the rest of the talk, just ignore epsilons. I mean, these kind of plus minus epsilons will be there everywhere, but you can ignore them, they won't really make our life difficult. It's just for writing the statements as formally correct, I need to write these epsilons. And sometimes they change between lines. Yeah.
I'm missing some. Okay, so on the left-hand side, we have some initial code. So this is, and these are like all possible symbols.
Yeah.
So a message would be a series of these things or something.
Yeah.
So every symbol is now encoded. So do we take, should I think, so when we say collecting, does that mean you send one symbol and then is it like yes or no? Or should I think of a series of symbols?
No, so it's sort of one big symbol. So when I say they collect, so this y sub r is now, let's say, again, according to some predetermined ordering, a sequence of d bits, which we think of as one single symbol. And two sequences of these d bits differ if they differ in any one position.
So on the left, should I think of there being a a set of symbols that are being set?
Yeah, so we have some code which was also on n positions. On the left, this base code C0, it had n symbols. Each symbol was encoded according to a code which was on d bits. So it sent those. And now on the right hand side, we again get n symbols, but now in 2 to the d alphabet. So this construction has two things. It has one big code, which is very weak, it doesn't need good parameters. And one small code, which needs good parameters, but it's so small that we can just brute force search and find a good one. And it combines these two to give you another big code. And this big code has as good parameters as this tiny small code, as long as the outer thing just had some sanity check kind of properties. Does that answer your question? Okay, good. Any other questions? Okay, so again, as long as the graph is a good enough expander and so on, you get a code, a global code, which is has n symbols and has essentially the kind of delta as 1 minus r, which is the singleton bound. So it does about as well as Reed-Solomon codes. But the alphabet size now is not a function of n, but only 2 to the d, where d again we think of as a constant. Again, because of this eigenvalue requirement, it will depend on epsilon and so on. So there will be some dependence will show up, but all of these are constants. And so these are codes which are actually used to construct, these are AEL construction is used to construct very good codes, which essentially take a local code on d bits, matching the singleton bound, and give you a global code. And the situation for this was a bit similar to Tanner codes. So we knew very nice, simple, unique decoding algorithms. In fact, I'll tell you the algorithm in 2 minutes. We could decode them up to Johnson bound using semi-definite programs. What I talked about last year is that they actually also achieve list decoding capacity. So they are list decodable up to 1 minus r minus epsilon, again, once you choose this inner code properly. And alphabet size is still constant. So these were the first kind of capacity achieving list decodable codes with a constant alphabet, where they can also be made in DPC and so on. So you can get, but the algorithm was still STP, and sort of I was still worried about being punched in the face. So we'll talk about a better algorithm. Okay, any questions? Okay, so let's do a warm up. Let's talk of, and so yeah, for these codes, now we can do near linear time again, this up to 1 minus r minus epsilon. So beyond the Johnson bound, we can do list decoding up to capacity in near linear time. And let's first talk of a unique decoding algorithm. So now let's pretend that the number of errors or the fraction of errors is less than delta over 2. So we can hope to output, in fact, let's say delta over 2 minus epsilon, just to sort of be on the safe side. And we want to output kind of one unique code word. So let's say we received X. There's one unique code word Y, at most one, which is in the ball of radius delta over 2 around it, and our goal is to find Y. We know X. So we have this kind of big code word now, or like this big list of symbols X. We want to find this big list of symbols Y. And we constructed this big symbols using these little symbols which are on the edges. Now we kind of just go in the reverse direction. So X has d bits for every vertex. They're not necessarily any kind of code words, they're just d bits. We kind of push them back, and now every vertex, every left vertex looks at the d bits on the edges incident to it. I mean, it's just the same bits on the same edges, we're just looking at them from the left. And we'll call this the local projection of X, or this X sub L, which is just a collection of d bits. And the algorithm is just, every left vertex will just try to decode what it sees. It sees this X sub L, it has this little code C sub n, which is just kind of on d bits, it will just try to decode. And what we need is that some sort of sampling property of expanders, or basically the expander mixing lemma, will tell us that for most left vertices, the distance between this local projection of X and the local projection of this unknown Y that we are trying to find will be the same as a fraction as it was between the big X and Y. Okay? We don't know why, but for any Y, this is true, that for most left vertices, the distances between X and Y locally will be the same, or like upper bounded by what it is globally. Globally, it is kind of delta minus 2, let's say delta minus 2, delta over 2 minus 2 epsilon, just to kind of, again, avoid any issues. So, almost every left vertex sees something which is within distance delta over 2 locally. And remember that distances again are the same for the inner code and the global code, again up to epsilons, but we are ignoring epsilons. Okay. So again, we can choose sort of this minus 10 epsilon here to kind of make all of that work. But for the local code, for almost all left vertices, the kind of it sees an X sub L which is unique decodable, which is within range, and it only has a code on D bits, so it can even take exponential in D time, it doesn't matter, D is constant. You can just brute force search and find some Y sub L. And because of what we just said, this Y sub L is actually the local projection of the true Y. Because in particular, we just showed that the projection of the true Y should be in this ball, and there can be only one thing in the ball, or at most one thing in this ball. So almost all left vertices find the right Y sub L, except maybe a really tiny fraction. But remember, the left side symbols also form some kind of a code. So if you have a very tiny fraction of errors, we can fix them later, and we'll not worry. But this is the algorithm, this is the whole algorithm. Just everybody looks at their neighborhood, does a decoding, and then they're done. I mean, like, we just call the outer code once. Any questions? Okay. So what we would like is something about as simple. And an issue is that when we try to do list decoding, everybody has too many choices to pick from. So now let's say we try to do the same scheme. So we have one X. Every kind of vertex on the left tries to look at the sort of symbols on the edges incident to it, the bits, and it tries to decode. But now the distance could be more than delta over 2, so maybe it will have to write down a list. Okay. And let's pretend that the lists are of size 2. The problem is already evident. Now everybody has two choices. There are 2 to the n ways of putting them together. Previously, like 1 to the n is 1, but 2 to the n is a problem. So we don't know how to kind of combine them. And this is sort of what we'll do, or we'll show how to do in near linear time. For the experts, you can think of it as a CSP and kind of solve it on expander graphs and near linear time using regularity lemmas. For the rest of us, including me, let's try to unpack that a little bit. Okay. So let's just kind of change this problem. Instead of finding these, like picking them, let's just kind of change this problem to finding a set of vertices. So let A1 be the set of vertices where the right thing to do is to pick the first element in the list. Again, everybody puts an arbitrary ordering on their local lists of size 2. And let's say A2 is the set of vertices. These are both unknown, by the way. But the right thing to do is to pick the second one. We don't know them. But equivalently, like instead of finding this code word Y, we can find A1 and A2. And again, even approximately is fine to an epsilon fraction error. So the problem is the same as finding these two sets. Everybody okay so far? This is equivalent to just list decoding. It's just, you can either make the choice or find the set where the right choice to make is the first one. All right, good. And now there is one nice thing we can notice about these sets A1 and A2, which we don't know, that they kind of stand out in a graph which we do know. And let's talk about the graph. This graph is just a graph where, let's say, we define the graph H1, where the first choice of the left vertex on that edge agrees with what we received on that edge. So we'll talk of, so this graph H1 is a graph, again, with the same vertex set, maybe possibly a subset of edges. So we'll take an edge in H1 if my first choice seems correct, at least on that edge. Okay. It agrees with what I received. So X has a bit on that edge, and my first list code word has a bit on that edge. If they agree, I'm going to take that edge. I'm going to collect all these and call them H1. Okay. Similarly, I can define H2 where the second choice seems correct, at least on the edge. But let's talk of H1. Everyone okay with the definition of the graph? This graph, I know. So that's the important thing about it. It's just even more local checks. It's like I know whether my first code word agrees with X on this edge or not. If it does agree, I'm just going to include this edge in H1. Otherwise, not. Everyone okay so far? Okay, and let's also define another set of vertices on the right, which I don't know, which is this B, where X is actually correct. So it's just the symbols which were uncorrupted. Again, I don't know which those symbols are, but I'm just defining it as a set B. Just to kind of write some notation, I won't really care about this B. All I care about is here. But B is now the nice thing to notice is that H1 only has a subset of edges. I didn't pick all the edges, maybe only a subset. But I will pick every single edge between A1 and B. Because if there is an edge which goes between A1 and B, because it goes to B, X is right on that edge. And because the left endpoint is in A1, the first choice was the right one to make on that vertex. Because on that edge, I pick an edge if kind of X agrees with my first choice, X agrees with Y, and Y is indeed the first choice because of A1. So every single edge between A1 and B is picked in this graph H1. But the problem is I only know the graph. I don't know A1, I don't know A2, I don't know B. The question is, can I find these anomalous set of vertices? So this graph is sparse. I only pick maybe a subset of edges, possibly much less than the entire set of edges in the graph. But there is this anomalous set between, like pair of sets between which I pick every single edge. And the question is, can I find this anomalous set of edges? Any questions? So now it's kind of getting closer to what expander mixing lemma did, kind of estimating edges. And now, okay. And in fact, I can prove what I'll call rigidity, which is if you find any set which has the right number of edges. So if you find any A prime such that the number of edges between A prime and B is roughly the same as the number of edges between A1 and B, then A prime and A will be about the same. This is like a two lines proof. It's not that complicated. Simple expander mixing. So then our goal is to just find some A prime which has the right density of edges between A prime and B, or like almost all the edges, which is in particular the same as what A1 does. If I can find this, I approximately find A1. Approximately is good enough. A small number of errors can be fixed by that. Is that okay? All right. So just need to estimate number of edges now. And this is where so-called regularity lemmas come in. In particular, I'll use a statement which kind of says that for any graph, which we are going to think of as a subgraph of an expander, there exists some fixed set of edges, let's say S1 to SR, T1 to TR, such that if I want to estimate the number of edges between A and B, I can just write it as a function of the intersection of A with these S's and B with these T's. So up to, again, a small error, which is small compared to the total number of edges in the underlying graph, n times T. Then some relation, yeah, so the graph has to be a sufficiently good expander. So for every epsilon, if lambda is less than equal to epsilon square, then this happens. These are known results. I mean, there is kind of a version of this for dense graphs by Fries and Kannan, and then there is versions for expander graphs. In particular, they can be proved using some abstract lemma from, at this point, a 17-year-old paper. And roughly so pictorially, you kind of say that you can think of this graph as maybe some linear combination of almost bipartite graphs. These coefficients can be very small. In particular, if the graph is n times d edges, then these coefficients will be like d over n. But this is regularity lemma. Thing to remember is that it lets us write density of edges as sort of functions of just intersection sizes. Any questions about the statement? And the sets S1 to SR, T1 to TR are just kind of known in advance. They only depend on the graph. They don't depend on A and B. That is crucial. So once you give me the graph, I can compute these sets S1 to SR, T1 to TR, and this coefficient C1 to CR. And so I can write down the second term just based on the graph. I mean, if I could compute the intersection sizes, then I can write down the second term. And this can be done actually in near linear time. You can write a simple, much simpler STP, which can do this in time n log square n. And in fact, if you modify this a little bit, you can even do it just with a singular value decomposition. You don't even need STPs. So you can do something simple. Okay. So now we have this set S1 to SR, T1 to TR. And now the goal is to find an A prime which has the same intersection with each of these sets, or roughly the same intersection as A1 does. Because the number of edges is just a function of intersection sizes. So as long as I find an A prime which has the same intersection with S1, same intersection with S2, and so on, the number of edges between A prime and B will be the same as between A1 and B.
R is small, I guess that's important.
R is small, so R is 1 over epsilon square. So it depends on epsilon, it's a constant, it doesn't grow with n. So I'll just try all of them. So I just need these intersection sizes, and again, it's okay to sort of say that the intersection size as a function of the size of S1, is it like epsilon times the size of S12, epsilon times the size of S1, or maybe for a different epsilon, but I can just kind of discretely enumerate all these intersection sizes. I'll just try all of them. One of them will be right because the set A1 that I'm searching for has some intersections. And so I will find an A prime with roughly the same intersections. Because of regularity, it will have roughly the same number of edges. Because of rigidity, it will be roughly equal to A1. And I'm done. So that's the entire algorithm. I compute these local lists. I reduce it to this question of finding sets in these graphs. The graphs take linear time to construct. The only non-trivial step is just computing this regularity decomposition, computing this S1, T1, so on. Once I have them, I just do a simple enumeration kind of algorithm, which takes, again, some constant times n time, or in fact, yeah, depending on how you define the time complexity, but it's certainly less than near linear. Okay. And that works. That actually can decode these AEL codes. Going back, the same algorithm also works for Tanner codes. Now there's kind of A1, A2 on the left, B1, B2 on the right. So sort of both sides do their decoding. Both sides has some lists and they have to kind of coordinate and choose together. So if there are like 10 things on the left, 10 things on the right, I'll define 100 graphs and do this. But it's the same algorithm. Okay. And just has these 3 steps. The only non-trivial thing is computing this decomposition, which is nothing new. It was kind of already known. So we just reduced it to a known thing. Okay. And as I said, it actually, if you set things right, it gives you new combinatorial bounds, new algorithmic results. It's also kind of a local to global technique, which kind of says that if these local codes have small lists, then you can get global codes with some bounded lists. And the previous result for list decoding capacity for AEL was also proved using some local to global, but needed stronger assumptions. And this one is a bit more robust. And one question which I really like is, I mean, the promise of these expander-based codes was linear time decoding. And for unique decoding, we knew this. For list decoding, now it seems like at least we are in the ballpark. So we are not talking of n to the 100 time algorithms. Now that we have n times polylog, can we get rid of this polylog? And this, I think, would be really interesting because we don't have any kind of linear time list decodable codes at this point. So, I mean, like even algebraic codes were recently shown to have near linear time algorithms, and this one also. And now, kind of, the question is what gets to linear time first? Let's stop there. No questions? Yeah.
So you mentioned regularity levels. Right. I was trying to parse it. So if you simply take normal similarity partition, at least in the approximate form, or you will get those things you need as members of this partition or not?
Not
How to prove it?
Sorry?
how to prove it, and its hidden question is how disasters are the constants involved.
Okay. So first of all, it's we only need Friis-Condon style regularity, not Summery style.
Which means single exponent or something.
Simple exponent. So the number of these sets is order 1 over epsilon square. The partition generated by them has size 2 to the 1 over epsilon square. But actually we can do a slightly smarter enumeration which only enumerates over 1 over epsilon square things. So you can even do better. So the constant is 1 over epsilon square, enumerating over them is a single exponential. Okay. How to prove it? So again, there are many different ways of describing the proof. I like to say the proof is kind of gradient descent. So one view is that you can think of this abstract setting where, let's say you have a function g. You want to find a function h such that the difference of g minus h is not correlated with any target function f for some f's in some function class. And we can think of them as this f are kind of functions which counts edges between pairs of sets. This G is the adjacency matrix of our graph, H is whatever we come up. Importantly, you can also choose a measure under which you take inner product. In Friis-Condon, you take just the product measure, you kind of just look at ij's, all pairs. When I'm looking at a subset of an expander graph, this mu will be uniform on the edges of the expander graph. But this lemma can work for any kind of inner product. Okay. And the proof is the following, that we're just trying to solve this problem where we are trying to minimize this functional
Maximum. You take maximum over
yeah, it's the maximum overall.
all tests.
So this is a maximum of piecewise linear functions, so it's convex. And it's a functional, it's kind of a function whose value depends on h. The true optimum is actually 0, you can take h equals g. And when we run gradient descent, it will get epsilon close to the optimal in 1 over epsilon square steps. And what are the steps? They are just in the directions of the gradient. What are gradients? It's a piecewise linear function. Every gradient is of the form fi. So gradient descent will convert, sort of create an h which is just steps in the directions of these gradients, and it will stop in 1 over epsilon square steps, which will have this property. You can choose your mu in particular. When you choose it to be uniform on the edges of the expander, you get the lemma dimension. Thank you. Yeah, I was wondering whether to put that proof in or not, but thanks for asking me. Other question? So you can decode expander codes using gradient descent.
It's not so bad.
Questions? All right, thanks, Madhur.